Hi, welcome everyone. I'm Olivier. Welcome to everyone to today's webinar. We're just going to wait a minute for everyone to join us and then we'll get started. It's okay? Good. So again, welcome everyone. In this session, we're going to explore exciting capstones projects and updates on Ada and Spark for the academic community. Please note that this event is recorded. The link will be available via email after the webinar has concluded. You won't be seen or heard, but if you're not comfortable with the recording, we invite you to sign off. I hope you stay with us. I'm Olivier Henley, GAP coordinator at AdaCore, and I mentor our capstones projects. That's what I did most of the past year. If you have any questions during the presentation, please use the tab at the bottom right of your interface. We will, once the talk is finished, we will ask those questions to the relevant team and they will be answered. Before we look at the capstones project from our academic community, let's start with some updates on a new development on Ada and Spark technologies from within AdaCore. I will now hand over to Fabien, who will explain more about this. Fabien, it's yours.
Hi. Oh, sorry. Disable this. Yes, so let me share my screen. I have some slides for you all. All right. Up. That should be okay for everyone.
Yes.
Olivier, good?
Yes.
Okay. Right. Let's go. Yes, so today I just want to take a few minutes to talk about some new technologies that are available for you GAP members and other members of the Ada and Spark community. So it's going to be mostly about ALIR and GNAT FSF. Let's dive into it. About ALIR, so we released the ALIR project released the version number 2 earlier this year with exciting new features like the possibility to install a crate. So it's going to build it and install it in a common directory so that you can use it as part of your system and just use the functionalities. There's a new publishing assistant that's going to be easier to publish your crate. Enhanced search with the ALIR search command. Another very important new feature is the shared builds, which means crates that you depend on will be compiled only once now instead of for every project where you use them. So for crates that are big, like the GTK Ada or libadalong that takes some time to compile, it's going to be a nice improvement in terms of performance. And we also have, as far as performance, the indexes that are loaded on demand now instead of just as a batch. So that's another nice improvements. This is just a short overview. Last week, Alejandro Mosteo did a nice presentation about ALIR 2.0 at the Ada Developers Workshop. So if you missed that, there will be videos online. You can watch it later. In terms of IDEs, we have a new release of GNAT Studio that's available on the GitHub. with improved code navigation, as always, and also some support for Alir now, so you can open your Alir crates directly in GNAT Studio, and many other improvements, of course. And there's also, if you prefer Visual Studio Code, there's a new plugin that was new version of the plugin that was released recently, with more handling for GPR files, integration with GNAT tests, and various bug fixes. We also have recently the new GNAT FSF version 14 that's been made available in the Alir index. So right away you can update your default to chain. So first you update the index with the Alir index update all command, and then you can select a new default to chain, so you can give it a try. And that's available for so Linux, x86, Windows, and macOS x86 as well. And we have a version for the ARM macOS machine that seems to work, so we're going to make that available very soon as well. For GNAT Proof, we are still working on the build. It's on the way. We are fixing some problems with dependencies on dynamic libraries, which makes it a little bit difficult to use, especially on Windows. So it's going to be available very soon now. We're just trying to fix some little problems with that. So stay tuned for that. All right, so now I want to talk about what's in GNAT FSF 14, in particular in terms of language evolutions. As you may or may not know, AdaCore is working a lot on the evolution of the Ada and Spark programming languages, and we have put in place some kind of a process where we first want to have open discussions about the new features in this GitHub repository. Then we and I invite everyone to join and have a look and make suggestions if you want to. We also after that, when we decide that a proposal is good enough, we go into experiments and prototype phase, where we try to implement this feature in GNAT, and the code is contributed to GNAT FSF. And so today I will have a quick look at the new features that are available in GNAT FSF 14 that you can use right now and try to use. To enable those features, what we call extensions, you have two switches: GNATX, which is for extensions that we consider stable, and GNATX0 for extensions that are more in a prototype phase and we don't know if we're going to keep them or not. Something important here, some of the features that are in GNATX0 for FSF 14 will be stabilized for FSF 15. So there's a little sign on the slide, you will see this. So let's go very quickly. First, fixed lower bounds for array types. So there's a new syntax over here. Oh, sorry, my bad. Where you can specify that the first index of an array or matrices and so on, it will always be, for instance, 0. And so as you can see here, I take a subpart of the array from 2, from 5, but in the print, it's always going to be 0. So I don't have to do m tick first. I know that for arrays of this type, it's always going to be 0. Dot calls for untagged types. So in Ada, if you want to use the dot notation, so object dot subprogram, this is in Ada today only available for tag type, and sometimes people just declare a type as a tag type just to have this notation. So in GNATX, you can actually have this notation for every type. String interpolation. So this is a templated interpolation of strings. So we have this special identifier here to say that it's a format string, the F before the double quotes. And then with the brackets, you can actually take the image of variables. You can even do operations, so x plus y here, and so it's going to print the result. We have the \n, \t, and so on in this feature as well. Default for generics formal functions. So that's one of the GNAT X0 feature that will be stabilized in the next release. So here you have an example. I can define for this generic parameter, the function copy, I can define a default implementation here as an expression function. When it's trivial like this, it's going to be make the instantiation of the generic a lot easier. Another XO to X feature is the ability to declare locals without a declare block. So as you can see here, the declaration of the constant is mixed with statements. There is no declare begin end construct. This is to as we said here, it's now considered a good practice to reduce as much as possible the scopes of variables. And this is just for simple declaration. You cannot declare a type, for instance, in here. All right, next step, a GNAT X0 feature. So we don't know it's going to be stabilized. The case pattern matching. So it's a new version of the case where you can match on the elements of a record, for instance. So we have a record with two fields that are integers. I can match when, for instance, here when both F1 and F2 are positive. So superior or equal to 1. Then I can match if just F1 is natural, so above 0, above or equal to 0, and F2 it doesn't matter, or the opposite, if F2 is natural and F1 doesn't matter, I can match, and then I have this fallback case. That's mandatory here because we want to keep the properties of Ada case statements that there's always all the cases are covered. In the same feature, so sorry about the syntaxing color, that's different, but we can also bind values. So for instance, here I can extract this parameter here, val. I can redefine it as v. So I match when has value is true, and then for whatever value of val, but redefined as the name v, and then I can use this new name v here to, for instance, return the value. And there's another way to write it here. All right. Some other constructs that are, so you may be familiar with the exit when struct. Construct, so you exit a loop when a condition is true. We extended this to other constructs like return, so you can return when a condition is true, return a value when a condition is true, for the goto, for the exceptions as well. All right, and I think I'm running out of time, so we will make the slides available. We have some other planned language features for Ada in Spark, so I will let you have a look at that. Yeah, that's it for me today.
Thank you, Fabien. Is there any questions for Fabien? You can write it in the chat.
Trying to look.
Yeah, thank you. I know that a lot of students will be happy with the new features. That's a given. Okay, good.
Okay.
So,
any questions? All right.
Yeah, sorry.
No, okay.
Let's wait a bit. Okay. Thank you, Fabien. Now, let's Joseph will Binyoum will present his autonomous Deminer robot. So, Joseph, can you take the stage and share your presentation? Thanks.
Hi everyone. Just
Hi.
give me 5 minutes time to share my screen. Okay. Do you see?
Yes, we see.
Okay. If I can turn to okay. So thank you for giving me this time to present the capstone project I've been working on. So my name is Joseph Binyoum, and I'm a GAP member and also a teacher over here in Dakar, Senegal. So I've been working on an autonomous Deminer project. When the first time when I met Olivier, he proposed me a project, but I came on with this project because of the context I'm in. So my presentation will be like this, and a little bit of abstract current context Senegal. Why the Senegal? The main goal of this project. Then I will be present the hardware, the wiring diagram, the 3D model, the software, the result, the resource, and then the conclusion. Okay, a little bit of abstract. So why a Deminer robot? Because of landmine. So what it is, a landmine is a bomb that is planted in the ground. The main purpose of this mine is to destroy enemy, and we can list different type of landmine, but for this I have only one to show you. The landmine, which is the purpose is to kill a human, and another one is anti-tank mine. The purpose is to destroy a tank in case in situation of war. So landmine is more than 100 million of landmine buried in more than 80 countries. That means we have a lot of landmine in this world. And according to the UN landmine, the estimation is about 50,554 people killed by landmine. That is a lot, actually. So landmine has a lot of impact, and it's not only by killing people, it is also by the impact in the biosphere. The landmine can destroy land. When people need land to make agriculture, is not possible. Also, the landmine can destroy water source, because it can contaminate the water with some materials such as plum or different kind of material. So their impact is really big for the humanity and also for the biosphere. Why the Senegal? The Senegal because I'm living here. And first, my first project was a small robot using the NST kit Lego. The purpose was to detect also a metal object. So when I first get in touch with GAP coordinator, the person of Olivier, I wanted to continue this project with some tools more professional. So I translated to my reality, the Senegal, and particularly the region of Kaserman. So what is Kaserman? Kaserman is a historic region of Senegal, located in the south of the country, because it's bordered by the whole river named Casamance. This region was, we have war in this region since 2000 and since 1990 till now, but now the war stopped. But this region was really, according to the UN, this region is about, we have about 1 and 2 million square square metal still remain infected by this man. Until 2014, we have 8 people were killed because they stepped on a landmine when they were going to a prayer. That means this region of Senegal is still exposed to this vulnerability, and this is the first purpose of this project, to help the GNO over here and also the government to fight against landmine. So for this project, I came up with a simple system, simple but not really simple, an autonomous deminer robot designed to use in dangerous zone or area. So the main goal of this robot was to detect landmine or metal object buried in the ground. And also the particular goal for this project was to reduce the mining cost. Because over here we still use human with a stick can search for the mine under the ground. That means they are really exposed to death. And one man on this field is another family, can be another son who will never see his father one day. I don't know. So this robot is here to reduce this cost and also to help to demine this zone faster. So here is the hardware and also the robot I came up with. This is the design and also all the equipment. For this hardware, for making this system, I use first a SCM32 F429 Disco 1. This development board has first it has a lot of a good RAM, about 256 kilobytes. Excuse me if my English is not very well because I'm a French speaker naturally. And also it has a LCD screen which you can see here, and a bunch of pins. Those pins help me to plug a lot of components. So, but for the component, I also use a battery. This is a lithium cell that comes from many old laptop batteries, because also in the context of this project, I wanted to recycle a lot of material as possible, because I didn't have a lot of money to buy all these things, and also those things come from the outside, and their cost is really expensive. That's why I use this lithium battery, recycling lithium battery. So for this project, I need about 13.4 volts. So I mix about six battery like this, because one battery is 3.3 volt and can deliver up to 200 milliampere. So to make the robot move, I need DC motor, but all those DC motor needs to be plugged to what we call a motor driver. And this motor driver has 4 channels. His name is L298N, and he has 4 channels where you can plug 4 DC motor and also another servo motor. And also I can power up my development board with this module. So I also need a sonar to detect object. This sonar is from Sharp, and his name is Sharp ER sensor GP2YI021YK0F. So this sonar was used to detect object while the robot is moving. And for the robotic arm, I use 4 of these servo motor. This servo motor has a huge torque, and also a huge torque means I can leverage around 10 kilogram with one. So I use 4 to make my robotic arm. And as the end effector of my robotic arm, I use this metal detector, not the whole stick, but the cycle part, which will help me to detect object and send the signal through this box. Okay,
Joseph?
here is, yes.
Joseph, just to let you know, you have only 5 minutes left.
Wow. Okay, here is my wiring diagram with the robot mix. Okay, here you can see the L2 298 with the power, and I also include a lot of wiring diagram for all the components. So I will speed up to go to the main part, which is the software I use to make this product. Here you can see the model. I made it with Tinkercad. This is the final version. It's not in plastic, but made with wood. So for the software part, the library I use was first the ADA driver library, which is provided by AdaCore and Ada Community. For this library, I also extended the library using another crack created by Olivier, the SCM32 FCAT29 Disco. And also, because it's hard to find a robotic project made with ADA, I found this project made in 2017 by Pat Rogers, Robotic with ADA. It supports me with a lot of examples how to get started. And I also wrote my own driver for the component I use, and you will see it in my GitHub repository. So this is the software architecture. I hope you can see it very well, but it's composed of 4 major packages. The position manager package, the sonar DMA package, and the scanner package, and also the vehicle package. So the vehicle package is the one who initialize every component from the different package. So all these package, the blue parallelogram you see here is a periodic task that will run on each package. So I have 5 periodic tasks, with each task has its own priority. So the position manager is supposed to call position manager and the GMA manager provide functions that are callable by client. All those functions, you can see them here outside here. And they are also functions that are within another package but is not used by clients directly. So the position manager has housed a noise filter, which you can see here. And this feature acts as a recursive moving average. So it smooth the digital signal coming from the sensor. What sensor? The quadratic sensor coming from the motor over here. And the scanner package, the sonars package, provide measure distance to the vehicle package. And the vehicle package use all those data to update the internal state of each motor, you can see here. So when the distance is less than that distance limit, which is 30 or 40 centimeters, the robot stops. And when it's greater, the robot keeps moving. And also the scanner package provide the detection measure to say if there is an object or landmine detected. Here is an application code source. And this courses is from the vehicle package, because the vehicle package really does all the business logic. Inside, you can see I instantiate 4 motor, which is for the vehicle. Also here, we have a distance limit of 40 centimeters. We have a period, which comes from another package called system configurations. So this package acts as a whole system configuration. Inside, you can find different priority for every task running in the system. So over here is a little bit small, but here is a task body named controller, which will act as a closed loop. So this task called 5 client function named get distance, get sample, and set internal state, and also get current position. Get distance comes from the sonar package to get the measure distance. Get sample, send the sample from each motor instance in this package to the position manager, so we can estimate the current position of each motor. If the distance is less than the distance limit, so we can set the internal state of each motor braking, so we stop the motor. Otherwise, we let the system running, and after then you can tell the motor to run or to stop relatively to this state. Also here we compute the average distance, and we check if it's greater than 1 centimeter, so we can start scanning. Otherwise, we do nothing. We keep moving if the measured distance is nothing. So here is a small demo of the robot acting in Okay, so after scanning, the robot can start. There is no object detect, or the distance the total travel distance is less than 1. Okay, this is a short video. Thus, of the robot. So here is the page of all the resources I use, and also my GitHub and the 3D model also. So for the conclusion, I will say the pro is I want to say thank you to AdaCore, because they gave me the opportunity to make this project become reality. I didn't have all the resources, I mean the material, also the expertise. For this, I had to do a part, so that is the pro training, Ada training for 1 week. It was very intense, so I want to thank AdaCore for this support a lot. Also, I want to thank Olivier because he was here. We have meeting sometimes 2 times a week, sometimes 1 time a week since more than 9 months from now, and I really want to say thank you also. Also, the good proof is, at the end, I can say I demonstrate that it's possible to make a robot over here using Ada in Africa, in Senegal particularly, because it wasn't that easy. It's a good challenge. I mean, I am, if not the only one using Ada over here. So for this project, I developed a lot of skill, and also I can create crafts for the future in order to contribute for the other community. And for the future, I want to upgrade this project by adding a direction wheel, a remote controller, and agree to remote visualization. This is the pro and my future expectation. So for the con, I mean, it was difficult to start this project because of lack of tool and also of robotic project made it Ada. And this is also an opportunity to contribute to the community. And also, being Senegal, it's hard to find development tools such as board, and also it costs a lot. That is the most difficult I found. And also, some component is not easier to implement in Ada. Maybe because I lack some expertise, so I need more time to work on it. Okay, so I want to say thank you. And this project is about 3,041 lines of code. So thank you for everyone to
Thank you, Joseph.
attention.
Great. Maybe we have time for one question if there is. First, I want to say thanks to you, Joseph, because it was a nice year. I think you did an amazing job. You learned a lot. I learned a lot. And yeah, I'm looking forward to what you will create in the future. It's good to see a project in Ada active. So nice. Keep up the good work. Okay. Any questions? Or one question? Pretty self-explanatory, maybe. Okay, good. So let's move on with Alan, Joe, and Xavier will present their bootloader. So I invite you to share your presentation. Hi, Alan.
Hi.
Hello.
Hello. Hi, Xavier.
So Joseph is actually sick today, so he won't be attending, and we'll be doing.
Okay.
Oh shoot, my screen share is broken. I can fix it, but I'll need a moment.
That's okay. No. I can check your collection of Star Wars.
Yeah, that's my dad's collection. He has quite a lot of figures on the wall behind me. Where is it? There we go. I don't know why it didn't work the first time. All right.
So, hello everyone. We are the microcontroller unit bootloader team from Penn State. I'm Xavier Zhang.
And I'm Alan Everett.
So now I'll be going over an outline of our presentation. First, we'll be going over some introductory materials, and then we talk about our project design and system processes. And after, we'll be giving a demonstration of our system, and finally, we will conclude with some lessons learned and future goals. To begin, our main goal of the project was to create an open source bootloader that was written in Ada. So this will allow us to showcase Ada in a bare metal environment, as well as utilize Ada's driver library. I'm sure you guys heard that from the previous presentation. Our objectives were to utilize pre-built drivers from AdaCore, as well as developing some of our own custom drivers, such as UART. We also wanted to develop a bootloader that's capable of handling the booting process, so booting the application code when it's not interrupted. And finally, we wanted the bootloader to handle microcontroller functions, such as erasing, flashing, and verifying.
So some intended use cases for our project was to make a showcase project for the Ada's driver library in a kind of real application instead of just a specific demonstration of a single functionality. The project also kind of acts as a good embedded example for Ada developers due to the low number of existing embedded projects. And this project might also be useful for corporations who want to have a solely Ada toolchain, since this bootloader fills one of the key roles needed for developing a microcontroller. This project, I'm sure you're all familiar with, uses the Alair package manager and the GNAT compiler. And then we chose to use Ubuntu and Visual Studio Code for a development environment. That just was easy to set up with the extensions for VS Code and Ada. And then we used GitHub to synchronize our code between the members of our team. For our microcontroller, we chose the STM32F746G Disco, which is a development board designed for STM32F7 microcontroller family, with many of the different features that the specific microcontroller on the board supports, such as the onboard screen and many different connection ports. Then we also use OpenOCD as a program to be able to communicate between our host computer and our microcontroller during development of our bootloader. Finally, for testing, we utilize SHUnit2, which is a bash-based unit testing framework loosely based on JUnit. This allowed us to kind of automate all the high-level user actions that not all of it necessarily was able to easily be ran from Ada, so we went with a bash testing instead. Next up, go over some of the project design. So our requirements was that this project ran on Ada-compatible microcontrollers, such as STM32 microcontroller that we chose. We needed it to be written in the Ada programming language. We wanted it to be invisible under normal operation. So if you didn't touch your microcontroller at all, it would just boot directly into the application code. We wanted our bootloader to be unique in that it wouldn't allow running corrupted software using some sort of self-integrity check. We wanted to have development host communication on the bootloader in order to flash new programs from a development host. And related, we also wanted to develop a separate command line interface program on the host to directly be able to interact with the bootloader without requiring some sort of unique weird setup. This is some of our system architecture. This diagram was initially our starting plans, but then we had to cut some things in order to fit within our time frame. On the left is the developer host application with the command line interface communicating to one of the microcontroller interfaces. We initially intended to have both UART and USB, but we cut off USB, so currently our bootloader only supports UART communication. Those interfaces are mirrored on the microcontroller side with the development interfaces. Similarly, only UART supported right now, which then will communicate to one of the loaders in order to be able to flash or verify our program. In this case, we only have drivers for the internal flash implemented so far, but it would be quite easy to implement additional loaders for external flashes, such as the onboard QSPI or an external SD card. And then finally, we also have our interaction package on the right that supports an onboard boot menu to be able to configure some options directly on the microcontroller.
And now I'll be giving a brief overview of how our entire system runs. So first, the user interacts with a command line interface and can send command through it. The CLI will then build a connection with the bootloader and send and receive packets through serial communication. And finally, once the bootloader, go back a little bit, yep. And finally, once the bootloader receives a packet, it will perform an operation on the microcontroller. For the booting process of the microcontroller, when it's initially powered on, it will check for an interruption, which is when the user button on the back is pressed within half a second upon restart. And if it's not interrupted, the control is then passed to the application code. However, if it is interrupted, the bootloader will then be loaded and control will be passed to the bootloader. And how we design the bootloader is, well, once the bootloader has been loaded, it will first initialize serial communication and wait for an acknowledgement message from the CLI. And when the bootloader receives an acknowledgement, it will send an acknowledgement message back to the CLI. And this is how we ensure the two-way connection between the bootloader and the command line interface. And now when the CLI receives the acknowledgement message, it will send a packet to the bootloader, in which the bootloader will then parse and process this packet and perform an operation on the microcontroller. And Upon completion of the operation, a status will be returned back to the bootloader, in which the bootloader will send back to the COI for the user to see. When designing the COI, we allow the user to interact with the system through several different commands. The user can call two types of commands, and the first type are the ones that communicate with the bootloader. So these are the verify, flash, erase, reset, and information commands. And the second type are the utility commands that only operate on the interface. So these are like clear, quit, and help commands. We will dive more into these commands and how they work in our system demonstration.
Which we'll be doing now. Now, I'm going to try and switch. Oh, can't switch from there. I'm going to switch my camera to, instead of showing my face, it should show our microcontroller. Maybe.
It's not working right now.
It's connecting. Okay,
okay.
There we go.
Yep.
All right, so in this camera view, there is both the main microcontroller, which you see taking up most of the screen, and then over on the edge is a mirror reflection of the backside of the microcontroller so that you are able to see the light. So right now, as you can see, that light is currently blinking, which shows that the application is currently running. What I'm going to do next is take our microcontroller and put it into bootloader mode, which then shows that instead. At which point I am able to connect to it from the host computer. So now we can grab some simple information, such as the information about the microcontroller. Sometimes this doesn't work the first time. There we go. At which point it reports the device ID and the hardware revision ID that's read directly from the internal configuration programmed onto the microcontroller's processor. If at any point you are unsure about the next thing to run in the command line interface, we also have a help command that lists all the available commands, and we could, if say we wanted to know how to flash the microcontroller, we could type help flash and get some detailed information on what the command does, how to call it, more about what the command does, more about what each of the options for the command does, and then we also added a section for any major revisions to how the command works. Next, I'm going to erase the current program on the microcontroller, which is based off of the hardware sectors that are able to be erased. So in this case, our program is living in sector 6 and 7. So if I erase those two sectors and then reset the microcontroller, you'll see it will return to a white screen, except for the LED. The green LED is no longer blinking. That LED was being blinked by the user code, so since the user code has been erased, it's no longer blinking. Next, we will flash that back on.
Yeah, make sure you go in bootloader mode first.
And as Xavier said, we'll put it back in the bootloader mode to communicate. Oh, come on, my thing came unbalanced. Is the framing's okay? There we go. So now it's in bootloader mode. We can. Oh, I forgot to finish typing command. So we provide both the file to flash and the memory address to flash it at, which this is the start of sector 6 I'm typing in right now. So then it'll read from the source file. It'll start by erasing the microcontroller to reset the flash to a writable state. It'll then write to the flash all the program data, and then it'll do a byte-by-byte verification to read back all the data and verify that was flashed successfully. So if that all passes, it'll automatically reset the microcontroller, and now, as you can see, our blinking light is back. Similarly, we can also run just a verification step with the verify command, which runs similarly to Flash.
Yeah, just make sure to enter the bootloader mode.
If we want to verify, and this would be useful if you wanted to just verify that the program was still correctly on the microcontroller without putting extra wear cycles on the Flash. And as you can see, it succeeded because we just wrote it, so it's not corrupted. Our CLI also has a few extra user convenience things, such as the clear command to completely wipe the screen, although the other commands are still there. And the quit command to return back to your host's prompt.
So now for conclusion, we want to go over some of the lessons that we learned, as well as some future goals of our project. And one of the most important lessons is to continuously test our system when developing. By doing so, this will ensure that our system is stable and working, which will increase our development efficiency. We also learned to utilize debugger tools such as GDB to make debugging our code quicker and easier. And finally, we learned to fix silent errors as soon as possible, because leaving them for the last minute will make it harder to find any errors produced when building the program using the Lear Package Manager. Now I'll be giving some examples of future goals that we had that we didn't have time to reach. First, we wanted to utilize the DMA peripheral for background memory transfer. And we also wanted to add an option to utilize the CRC peripheral for verification instead of our current byte-for-byte verification method. And finally, we wish to add new ways to interface with the bootloader, including an onboard boot menu as well as an alternative serial boot menu. And thank you, everyone, and we're now open for any questions.
Thank you. We have a question from Martin Marcos. How difficult would it be to migrate to another MCU?
Let me switch the camera back so I see my face instead of the other thing. There we go. So that would mostly be the responsibility of swapping out a bunch of the hardware drivers and the associated abstraction layer for said hardware drivers. If you're going to another STM32 microcontroller, I would expect this to be very straightforward due to the incompatibility of the APIs of STM32 microcontrollers, as long as it's one of the ones that already has stuff written by Ada. In this case, we were writing a bunch of the things for our specific microcontroller from scratch. So those same layers that we written for scratch for some of the other microcontrollers would also need written from scratch. Some of them are implemented for like STM32 F4, but it's still a emerging domain for Ada.
Good. And another question, is it open source? What license have you chosen?
It is open source. I believe we have yet to put an official license on it, unless there's a default license to all the things in the GNAT repository, or in the academic repository.
Yeah, you can view it on GitHub.
I think when you create an Lear crate, you have to choose a default one is set, which is either Apache 2, MIT, or something. I'm not sure. Maybe Fabien knows more about that. But anyhow, no state secret there. Yeah. You can fix that in your repo and make sure people can reuse it, right?
Yep. We'll probably try and get a license on that here soon.
Good. Thank you. But would you say that if you were to use an Lear chain with the proper HAL set, it would be pretty straightforward to port to another MCU?
I believe so. As long as as long or as more microcontroller projects become developed and more of those drivers are implemented, as long as they're following the same API as the current drivers, it should be fairly simple to add those in as an extra option.
Right. So we might need a specific implementation of the drivers, but that's the only thing that would be missing.
Yeah.
Okay. Good. Thank you very much, guys. Any other questions? Yeah. Good. Great. Okay, so let's move on to the next team. Next team is going to be Anthony, Kien, Mason, and Robert, who will present their RINA stack. Thank you, Alan, Xavier. Thanks for all the effort. It was great working with you.
Do you know how to leave the stage?
Click. Right, good. Hi. Oh, take the presenter mode instead of slideshow. I think it shows wide bigger on the screen. Okay.
Cool. So thanks for everyone for joining us on our presentation of the bare metal recursive internetwork architecture stack. I'm Kien Kaserman. I'm joined by my teammates Mason and Anthony. So a quick outline of our presentation. First, we'll go over our background and objectives. Then we'll show you the architecture and the user interface design. And then finally, we'll end it with showing a little bit of a demonstration of our system. So why does our project need to exist? Well, mission critical applications need performance, secure, and reliable networks. And this relies somewhat on the architecture of the network. So the current standard of network architecture is TCP/IP. And it's been criticized for the following three reasons. There is somewhat of a lack of efficiency because of the overhead of a lot of the protocols in TCP/IP. Additionally, TCP/IP never integrated security directly into the networking stack. So you have to almost bolt it on with things like IPsec after the fact. And finally, there's an issue of complexity. So TCP/IP's layers are pretty tightly coupled, which makes it pretty complex for implementers. And there's also many different data formats, or the different data formats make it more feature rich, and this creates more complexity.
So I'll talk about some of the objectives of our project. As we mentioned in the first slide there, our project was to implement something called a RINA stack, which stands for Recursive Internetwork Architecture. And kind of what Kien mentioned, this architecture tries to solve some of the pitfalls of TCP/IP, which is the current architecture that basically the whole world is running off of. And RINA kind of brings like a new sort of idea to what was previously done in the TCP/IP stack by proposing the theory that networking is basically inter-process communication. And so when we talk about sending data between two network devices, we can kind of think of it really as just transferring information between two processes as if they were on the same computer. And so RINA, part of the architecture is that we just consider everything as IPC. Another part of RINA is that we have a single communication protocol instead of several loosely coupled ones, which is, of course, one of the criticisms that Kien mentioned as well. And so our primary objective was to develop a RINA solution in Ada, not only for a desktop device, but specifically for a bare metal implementation. And so for that, we chose to do this on the STM32 F746 Discovery development board. There's a picture of that at the bottom right, what the board looks like there. And if you notice at the very bottom, we left this figure in at the bottom left that shows kind of what TCP/IP looks like today. In theory, you have your traditional 5-layer network stack, where you have your physical link, internet transport, and application layers. But you end up with kind of these intermediary protocols and layers that kind of try to fill some gaps in between. And so it's kind of got this interesting problem where these protocols have kind of, in some ways, become their own layers, departing from the traditional 5-layer design. Something Kien mentioned, like IPsec, for example, wasn't an inherent feature in TCP/IP, and so that's kind of just spawned as an intermediary thing. And so what RINA tries to do a little bit differently is instead of having set number of different layers, we have what are called diffs, which are distributed IPC facilities. And these can be stacked in as many layers as needed, depending on your specific application and your network environment. And those can be actually made recursive, part of the recursive nature of the architecture. And so you can actually fit multiple diffs inside of each other. And you can build some pretty complex network architecture by doing that. And of course, our secondary objective of the project was to basically challenge all of ourselves to develop some new skills. None of us have ever worked with the Ada programming language before the project, and so that was something we wanted to work with. Also working on some low-level stuff in bare metal as well was also something new for us. And also, build and try to redefine some new networking concepts. So just looking at our system architecture from a pretty high level, when we first came into the project, we wanted to see if we could find any existing RINA implementations, because RINA is kind of been limited to some academic research. We wanted to kind of understand what does an existing implementation look like. And so we found one called RLite, which is a C implementation of RINA, a lightweight C implementation. And so to prevent having to dig really, really, really deep into lots of documentation, half of our system is essentially a Linux build, which provides an API interface layer that we wrote in Ada that wraps around RLite. So we're allowed to basically communicate with RLite's RINA implementation. And so this provides us a RINA stack on a Linux device or an Ubuntu device. And through this, we can communicate to our STM32, which has its own RINA stack that runs in bare metal. The reason we did this is because each of us only had one board. And so naturally, without having two boards, we can't have them communicate with each other. And so the way we got around this was basically build a stack in Ubuntu, build another stack on the bare metal board, and communicate between those two devices there. And so the right half of our system architecture is what actually runs on the microcontroller. We have the basic Ada drivers library and the abstraction layers that are provided by AdaCore and Fabien, I believe, wrote. And so a lot of the heavy lifting, the very low level stuff was already taken care of in the board support package and things. However, we add our own tasks to the Ethernet receiver, so we can take packets coming in and manipulate those, so that way they're in what we call an error and flow control protocol. And those messages we translate into flow messages or data messages, depending on what they are. And we have a diff manager, an IPC manager that can basically take the data out of those packets, determine what it needs to do with those, and transfer the flow to the specific application running on the board. And so you can see that kind of the natural flow is you have an application running on the Linux device, and it's able to transmit a packet or some sort of data through Linux, over this error flow control protocol over the wire and onto the STM device, which then routes into the application running on there. So I'll pass it over to Anthony. He'll talk a little bit about the UI.
All right, thanks, Mason. Yeah, real quick to go over our UI design, which we'll see here in the demo. With the board itself, we used a board resolution of 48 by 272 on the pixels. And the main objective here was just to display the RINA network statistics and also act as a screen debugger to display warnings or any kind of errors. So this is our initial UI mockup, and you can see kind of what we were going for. Again, with different menu options, seeing exactly what we're connected to. And then if anything were to go wrong, we would get that error display or some kind of information to let us know exactly what's happening, not just that it's happening and we can't see what's going on. So next slide. And this is the actual display here from the screen we took. And so again, we're just seeing that it's receiving packets and the information of how many packets have been received, the data that's going through, and then we can see we're connected to the board. There's also a couple other buttons. It is touchscreen, so we did enable those so that we can check the file browser, and which we'll see here again in the demo, where we can send a file to the board over the RINA stack, click to view anything that we've sent. So again, just a quick overview of that, just so we can go into the demo and actually see the board in work.
Thanks, Anthony. And with that, I will share the demo video. Just give me one moment. So now we're going to give a brief demonstration of our system and how it all comes together. If you recall from our previous slide, giving our high-level architectural view from our UML component diagram, you may remember that our project is split into two distinct components, if you will, two separate builds. We have a Linux build, which interfaces with RLite. RLite is a RINA implementation written in C.
Can't see. I don't see an image. Does people see something?
In C.
It's just spinning for me.
I see it on my screen.
Oh, okay. Sorry.
No, some people see it, some people aren't.
That we are using in Linux. See this?
It's good now.
Now I see it, yeah.
Then we're going to give a brief demonstration of our system and how it all comes together. If you recall from our previous slide, giving our high-level architectural view from our UML component diagram, you may remember that our project is split into two distinct components, if you will, two separate builds. We have a Linux build, which interfaces with RLite. RLite is a RINA implementation written in C that we are using in Linux. And we have built in an API interface layer on top of RLite so that it can be used for Ada programs written in Linux. And we have a build for the STM32 discovery board, which also has its own lightweight RINA implementation. And so what this allows us to do is to have the RLite RINA implementation interface with our own RINA implementation, and that way we can actually transfer data between two devices, since we only have one embedded board per person. So the first thing I'm going to do is configure RLite with the right diffs in order to actually support the demonstration we're going to give. So the first thing I'm going to do is create an IPC process. We're going to call it ethab.ipcp. And we're going to consider the Linux machine to be node A and the embedded board to be node B. I'm going to go ahead and likewise name the diff that this IPC process holds. I'm going to name it ethab.diff. And the next thing I'm going to do is I'm going to configure this diff, or configure this IPC process rather, to map to the network interface card for the virtual machine. And this just basically tells it, whenever we receive information to this IPC process, we receive information on this diff, we want to reroute that traffic, since it's an Ethernet shim, to an Ethernet interface. So I'll set up that configuration. I'm also going to create a second IPC process and a second diff. And the reason we do this is because the Ethernet shim is, as the name implies, acting like a shim. So what we'll do is we'll have a normal diff that whenever data is sent to this diff, the shim diff will be registered, so that way this information will flow from the normal diff to the shim, Ethernet shim, and then out over the network. So as I mentioned, we're going to go ahead and register this to ethab.diff. We're registering our normal IPC process to the Ethernet shim diff. And finally, we are going to enroll. And this is what is going to send out all the requests and flow information in order to link the Linux device to the embedded board. So before I do that, I'm just going to go ahead and clear out the Wireshark just so we can see what's going on there. When I go ahead and hit enter to enroll, you'll see we got this message here that enrollment was completed successfully. And you'll also notice on the board we had a bunch of things happening. We had a bunch of Ethernet frames were received, a bunch of Ethernet frames were also transmitted at the same time. I will hit stop on the Wireshark just so we can kind of step through what actually happened here. The first thing that it did, Arlight did, is it sent out an ARP request looking for b.ipc process. And you can see here that it does some things. It stretches the definition of the address resolution protocol by, instead of using IP addresses, since we don't use IP addresses in RINA, it replaced these with ASCII characters with the names of the IPC processes. So this request was broadcasted to all devices on the network looking for this b.ipc process. Our embedded device saw this request. It, internally checked, do we have IPC process called b.ipcp? And it did. So it sent an ARP response telling the Arlight side of things that we exist at this MAC address. The next thing it did is it sent some policy-related information, and this is encoded in something called protocol buffers, which we discussed a little bit earlier. And these protocol buffers encode what we call CDAP messages, which is a common distributed application protocol. And this, again, is a serialized object, essentially, containing all the information related to policy. So if I step through, some of it is in ASCII text, so we can kind of read it. You'll see it communicates back and forth these objects that define things such as link state, distributed policy information, as well as things like keep alive times. So, for example, how long do we wait before we consider a device stale? Consider the connection dead, if you will. And so a bunch of these pass back and forth, and so we've had to actually build all of these messages and send these responses. So I'll move over to the actual embedded board again, just so you can see that. You'll notice that we have this menu button here, and this menu button allows us to toggle some of the information that we see here at the top right. So we just have a basic stats that just show the metrics such as the throughput of data that's coming in. So we know how many packets are coming in, whether we're transferring or receiving, which are indicated by those lights up there, and how many packets that we've received. So if we go ahead and hit this menu button, since we do have touch functionality, we can selectively toggle these menus. So I can turn the network stats off and that will disappear. I can, of course, re-enable it by hitting it again. You'll notice that we also have this file browser. So if I go in there now, there's actually no files, you'll see, because we haven't sent any data yet. So I'll actually exit out of this menu, and we're going to go ahead and transfer back over to the Linux machine and try to send some data. So first thing I'm going to do is open up a program that we've created. It's a program created in Ada, and it uses our Arlight interface layer. So there's a bunch of Ada code being ran here. I'll go ahead and run it. And this is just a basic demonstration program that allows us to send an image over to the embedded device. And currently this only supports bitmap files, .bmp. So I'm going to go ahead and grab this file here, this adalogo.bmp. And you can see we got a nice little preview of it. It tells us the size, which is quite big. And we're going to go ahead and hit transmit. However, before I do that, I will reopen Wireshark. We will start capturing again. And I'm going to go ahead and transmit this picture. And when I do that, it's going to tell me, well, this image is too large to be sent in a single Ethernet frame. This is kind of just for debugging purposes. And so we're going to need to split this up into multiple Ethernet frames, obviously. So I'm going to hit OK. And you can see a bunch of Ethernet frames just sent through. And this is the actual BMP. This is the actual bitmap image. And you'll see on the embedded device, we actually are tracking. It tells us how many of these packet frames we've received, and it tells us exactly how much data we've received. So moving back to the embedded board, now if we enter our file browser, you can see we have a new entry there at the top left. It no longer says no files. And this is the name of the file that we sent, ada_logo. So if I go ahead and tap on that, you'll see that we now have the image that we sent to the device. So this is just one of the many possibilities with RINA. Obviously, this is just a very simple example. You can build plenty of complex demonstrations, but given the limited time, this is just a simple one that we came up with to demonstrate it. Cool. So I believe that concludes our presentation. If anybody has any questions, we'll gladly answer them.
Thank you. Well, yeah, it's an amazing job, seriously. It's and sending the image is just the icing on the cake. Yeah, really, congrats, guy. Thank you for all the efforts. It was a intense year, but you nailed it. So, anyone? I want to build a router one day using your stuff. Anyway, anyone has questions? I invite people to go read on the theory of RINA. It's very interesting. Flexible. Yeah, there's a lot to say. There's even a book written about it by John Day. Okay, so it looks like there's no. Yes, thank you, Ahmed. As there's no specific questions, we'll move on. I'm the next one. I will present a GNAT update from the last year, what we did. Okay, so let me share my slides. No. Good, everyone can see. Perfect. I'm going to try to speed it. I have a lot of things to say, okay? Here we go. So this year, the main focus of GAP was about the capstones. Why? Because I want, at AdaCore, we discussed about it, and given also my inclination and talents, it was more about doing concrete stuff, applied stuff, and try to advocate Ada through usage, okay? So the motto I'm trying always to go forward is fun, challenging, and impressive. I'm a big fan of going back to the fundamentals, trying hard things, low level, and discovering, I don't know what's the magic that is behind everything high level we use every day. I think Ada is awesome for that. It shines by clarity and whatnot. Why am I getting big? Okay. So it's really also an holistic experience. What I mean by that is it's a reduced life size experiment. A project is there's so many moving parts, right, that you have to adapt there. And the next point is it's a real stress test of Ada and the ecosystem. It's also, it's linked again, it's like eating our own food. So I'm like outside in the world, I say, yeah, Ada is nice, it's nice. Okay, how does it hold up in a project with all the faces of what it entails to do a project, right? So yeah, we run into many things that are nice, awesome. Some are less nice. It depends. So a real stress test. Resources presents in the wild. Students are ruthless because they're used to something. They're fine. It's nothing is their fault. It's just that they have expectations, right? And it's totally normal. The world is at the Python and NPM duck level and or usage. So how do we hold against that? So the most important lesson for you guys is Slack is for old people, and Discord is in complete domination. It's no joke. So just so you know it, and don't say that you use Slack and be proud of it in cocktails nowadays. It's okay. You can use Slack. I use it all day. It's for old people. So that was my joke. Maintain a list of capstones on GitHub for the next semesters. This is my way to share and expose and maintain stuff. Okay, moving on. You understand that those projects, when I approach them, we need to get up to speed fast. So here I want to indicate to people that somehow we have some preferred gap boards. When I mean development boards, right? The key evaluation is affordability, availability, brand relevance. Why would I choose Renesas when everyone is doing STM32, let's say? Nothing against Renesas. Support maturity, reasonable features, and this is not set in stone, it's just logical, okay? So what it means for you, if you plan to do something with Gap, there way less friction if you target those boards, because they are kind of ready. Okay, they were in the driver library. Those are the ones that have the most code and or drivers ready for it. So there's no way to kind of we can try other boards, no problem. It's just we will need to put more love, more work. Okay, so those are pretty capable. They're pretty overall, they fit many builds, so I go with them for now. If always open to exterior help. Okay. No, Gap is not for members. No, not at all. There's a project that is native coming in. The microbit V2 is one that we want in the lineup. Stephen Buss did some great work, but we need to experiment around it to make sure it's more, everything is fine. There's no friction. I cannot lose time with showstoppers when I embark with students or capstones. Okay. Here, what I did to onboard, again, I created an Alire chain for both boards, the F429, F746, effectively porting relevant ADL code, so you don't bring all the other driver library code, just what is needed. It's in part the goal being so that I can, I don't know, better navigate and explain stuff to newcomers, which are students, right? So Cortex-M, HAL, STM32 HAL, this is kind of a new crate that has almost everything. It goes on to the two different boards. And then I have a Blinky demo and a draw demo that works for both. This is really just to, again, Alire build those and build those so I can start talk with students directly about the layers that are implied to build an application. We have something we can see and we can use. Okay, so they start from there. The estimated date for microbit V2, I don't, you need to put the time on it. I've people, Daniele started some stuff. I need to get around. I have no dates. Sorry. I also started Ada for the Impatient. This is a working project. I call it AFT. This is born from lack of commitment to go through Learn Ada by students. Okay, this is just, it's not me. I don't want that. It's just a fact. It's not because Learn Ada is not well done. It's awesome. Okay, just they have a lot of courses. They're interested in producing something, and they don't have time to read lines and lines and lines and lines. It's not that it's that much. Compared to Barnes, it's so reduced. What I mean is that my goal is to try to maybe, if I had to teach them a lot. Okay, like I had to go over Learn and kind of condense in my own words what was said there. So Learn is a kind of a good in-depth, if I would say, the best bang for the buck, in-depth initiation to Ada. I need something that goes even faster. Okay, so I try to inspire from Learn X and Y minutes. So it's organized as a collection of short ADA tricks of the trade. It's core code and short comments, period. Okay. I want to thank Luke Guest, I think, that did the Learn X and Y for ADA. So this is my starting point. I guide them through ADA basics fast because they all know other languages, right? So we go. I try to focus on illustrating what is useful and what is peculiar to ADA. Also, we did. There's two projects that are not here today. There's one from Université d'Ottawa. It's an RSA public key crypto lab. So really, it's this one is GNAT native. Okay, it's two clients, Alice and Bob, two instances of client, one multi-threaded socket server. This is wrapped in Immekus. It's fully functional as a public key exchange. It doesn't use the standard way of exchanging. It just exchange stuff, but there's a kind of mini state machine that provides, the exchange. You can see the visual simulation, so you can see in the server, you can see that it sees only encrypted stuff. Okay. And you can see also that both clients receive the decrypted message that was encrypted on the other end. It uses the big integer from latest stuff from AdaCore. The keys are only 2 bytes long, so this is not secure at all. But it includes implementation of all core RSA algorithms, so it's very fun. I need improvement. I need implementing larger keys. I might have a prospect for Capstone in fall 2024 from Ottawa, and also creating the labs with parts left for completion debugging by students. So something I cannot give them the whole product finished. It's not the point, right? If you want to do a lab, you need to complete stuff and improve. So this is not done. Also from University of Ottawa, a real-time embedded lab. So Chen Yuan Ma, Yuan Yo Zuo, William Wang cannot be here today, but what they did is they use STM32F4, 29, and basic electronics. So a LED, a buzzer, light detector, I think, yes. And they did 5 labs real-time with real-time notions in it, okay? 5 different labs of purely in ADA using the Alir chain, and those labs are like street traffic lights. Okay, how do you do some patterns using timings? This is like the first lab. The second lab is an alarm system. The third lab, etc. Okay, so. So yes, this was proposed by Mr. Mohamed Ibrahim, professor at University of Ottawa, and he wants. The plan is to have this lab officially used at University of Ottawa, and there's a lot of traffic there. There's like 150 new students each year take this lab, so it's a good way to showcase them by usage of ADA, right? So it needs to show it works well. That's my main goal. So the labs are operational. I made sure that I went with them, we built it, everything worked properly, but I need the instructions needs to be refined. I need to do a TA version, so the correct answer, that kind of stuff. It's not that long, but I still have time. It's for next winter. So the main goal of GAP is to expand the labs into a comprehensive pool, share with universities. So something curated, right? There's a lot of engineering fundamentals and CS that can be solidified through these lab sessions. This year we went to 60, 20, 24. We presented the RSA public key simulation, the embedded Flexbox that you will see later on from Penn State, and the AdaScope, a project from last year. We did many new contacts. Tulane is very interested in doing capstones. I talked with the professor 2 times already. Simon Fraser, Canada, Max Planck, UC Berkeley, Northeastern, and many more. 60 is very CS oriented, okay. Professor Samud told me about the equivalent for engineering. Next year we might check that more, because the applied project, the capstones, are way more, how can I say that? They were of interest mostly by engineering people. Okay. So a huge thanks for Caris and Alexandra at AdaCore who helped me, and Alexandra came with me there. So it was a blast. And yes, cannot make it without them. Moving on, I went to the 2024 Fessenmeyer Engineering Design Conference. That was all at Penn State, Berend. You see a lot of those projects today. The capstones were, what is it? The Bootloader, Flexbox, RINA, and ML Engine. Yeah. So this is an initiative led by Prof. Ahmed Samoud. A big thank you. He's here today with us. And there was a special guest, which is Greg Simon, VP of Engineering at Google, leading Fuchsia OS. And he attended because all talks were like in parallel. You could not attend every talks. There were just like a bunch. But he chose the Ada bootloader presentation. He was with us. It was very nice. I'm still waiting for the call from Greg. I spoke to him, but no. Not interested yet in Ada and Spark. Sorry. We also are sponsoring CANSAT France 2024. So this is a satellite competition in France. It's EPITA Paris Evolutech students. The deal is we sponsor that. It's 100% Ada for programming the CANSAT. They did key activities. They attended the Pro Ada training, and I kicked them off with a pressure sensor implementation, the BMP 390, to show them how to use Ada as a low-level programming language and all the marvelous things it provides in terms of expressivity. So the missions are mark the zone around the GPS point, land upright, create and integrate a sensor to measure physical variables. So this is a homemade sensor they need to do. And they need to deploy a flag autonomously when it reaches the floor, the ground. And they need to undertake one or more mission judged on originality, blah, blah, blah. So I'm with them. This is this summer. You'll hear about it, except if they are last in the competition. Yeah. We're sponsoring Space Concordia. They do a CubeSat SC Frere project. The launch details is they're partnering with 8 Canadian universities, scheduled for early 2026. The mission objectives, it's capture, process RGB Earth image on board, and investigate yeast growth. Now, bad news, Ada was postponed, deferred due to time constraint and complexity. And because seriously, I think we're pretty equipped to help them get to speed. It's hard. We cannot be there all the time to help them, right? They have their own dynamic. They used to have other code. They don't know Ada. Nobody knows at the university. It's a kind of thing. This is a work in progress. How to, keep the interest and or the good stuff alive, if I may say. I'm working on it. Okay, open-ended question. The framing. When I say that 2024, 2025 framing, it's my framing, the mind framing, like I would say, as the open goals. Okay, accelerate student onboarding. When I propose a project, it needs to. They want to do the project. They don't want to learn a new language just to learn a new language. Okay, they want to use it. So that's why FT, the gap alley creates so that things are way easier with a package manager. They already know about it. They use NPM, they use pip, they're right. So all the good stuff. I want to enhance Capstone's project, so closer to students' core interests. I want them to be motivated. Not that it was not good last year, it's just that sometimes I'm like, yeah, okay, it's more. Let's get some empathy and say, when they are motivated to something, they will do amazing things. That's the key here, and still be aligned with GAP medium-term vision. Shift to engineering events, and I want to help cross-pollination among GAP members. This is super important. We have some theme, right? Let's see. You saw we have one CANSAT, one CubeSat. We have Vermont CubeSat. We have it's our space. Space is Ada space, right? So an example would be an Arduino ecosystem for student space projects. So maybe use capstones to produce stuff that would help space initiatives. You see my point? So coordinate around advanced open source project. We have amazing projects in the Ada community. I think about Ironclad, HiArtos, Orca, to name just 3. I think the more we use Orca in the ML engine, you'll see later, the more I can reuse those and build upon, it's good for feedback and also awareness and that kind of stuff. Coordinate around relevant industry technology. Sometimes I'm at AdaCore, I see we have a lot of clients that do amazing stuff. Sometimes it's far away from the more popular technology, right? So, but if there's an opportunity, why not bring those tools and or into the loop? So Geisler is doing open source configuration SOCs, right? So Leon, Noel, RISC-V, also maybe SpaceWire, the kind of stuff that is used by our clients, I could try to put projects around that. Capstones as a formative boot camp, prepare students with industry relevant skills like the Leon processor. At least they can put it on their CV. I know how to get my way around that, the lingo, everything. And continue to deepen the understanding of academic and industry needs. That's the goal of GAP, I think, in relation to AdaCore and Ada, right? So that's it. Thank you for your attention. Anyone has questions for me? If you have comments, ideas, discussion, don't hesitate to write to me, okay? Yep. Okay. Thank you, Fernando. I'll go up and see if we have more questions, because I think there was a lot. GAP always for, no, I said. GAP is not always for embedded only. Microbit, no date. Thanks to Word. Yes, Ada needs to get in more college and schools. Okay. Yes. Yes, definitely. LibSDL could do something around that. Would be interesting. Good. Thank you very much. So now, are we on time? So it's 11. Let me check something. A bit late, but I had some. Okay. So let's move on. We do have Owen that will present for the ML Engine team. Sadly, he's alone because the other one have jobs and could not be with us today. Owen, can you share and take the stage?
Hello, Olivier. Thank you
Hi.
for the brief introduction.
Marta Marcos has a question. Does GAP include postgrad academics? Yes, it does. It's an entry point that was not there was few or how can I say that, no traction, okay, for me this year, but yes, would be very interested in doing postgrad stuff.
Okay, so good morning, everyone. I'm Owen Wienczkowski. As Olivier had mentioned, my other teammates could not be here today, unfortunately, but this is the Ada machine learning engine. So I'll start with a brief outline of this presentation. I have provided this outline to cover what we'll be discussing here. So first I'll cover a basic overview of the project as well as neural networks and then the techniques my team used, and finally our experiences and challenges followed by the applications of this project. So first, this project is really based off the grounds that before this project, there was no implementation of machine learning within Ada. This was an issue because the industries that primarily use Ada, as well as all industries at this point, are starting to trend towards machine learning and needing to have machine learning and AI within their projects and within their processes and services. So all these organizations were left with the decision to either choose what languages they currently have, and if that's Ada, to then either start being without machine learning or to have to convert to a different language that can leverage the machine learning techniques. So the task of this project was to bring the machine learning implementations into Ada and be able to make a neural network natively. So this project has one key objective, and it's to develop the foundations of machine learning within Ada. And to do so, we define this by engineering the necessary components and functionality to construct and train a neural network using Ada exclusively. So by having the neural network functionality, we're describing that we must be able to train a network thorough enough to where decisions are clearly being made. In this case, we decided to classify our assessment as the neurons being able to classify different groups for a spiral decision boundary. And what a spiral decision boundary is what's here on the right-hand side of the screen. We have 3 different groups of classes or points, and we tasked our model with being able to classify which group each point belongs to, or if another point were to be added, which group would be belong to. So that's why there's the different lines on the chart, is to show which decision or what decision the model would make. So for context and a bit of background information, I'll briefly review neural networks. So neural networks are constructed on what are called perceptrons, which reflect the neurons of the human brain. So these are the building blocks that typically consider multiple inputs and mathematically produce a singular output. So each of these perceptrons, or neurons, represent the model's perception of a feature within the data set. It describes what the model sees, or it gives a numerical or mathematical value to different key elements within either an image or within a data set, just the points, different areas. So these together form what's called a neural network. The outputs from these neurons can heavily vary in numerical value based off of the calculations used to determine what these values are. So to simplify the meaning of what that decision results to, we pass the values through what's called an activation function. And this instructs each neuron to either activate and be included for the decision, or remain quiet, which would express that the feature that this neuron represents is not necessary for this decision. You can think about this as if you're trying to identify features of an animal. If you see 4 legs on the animal versus 2 legs on the animal, then a certain neuron would light up versus stay quiet. And this would help the neural network make its decision. So our relevant techniques for this project, we decided to engineer our machine learning engine using the Olivier package manager, such that users could use the package manager to manage our software into their projects. And for our components, we decided to test them using AUnit. And by testing our components, doing unit testing, integration testing, and overall system testing, we can ensure that our project is stable and safe to be used for neural networks in the future. So for our engine, we then decided to go and engineer each component specifically, such as the activation function, which I spoke on earlier. In our case, we decided to use the ReLU activation function, which takes those output values and does not affect any of the positive values, but brings all negative values and 0 values to be equal to 0. This way, we're not worried about excess magnitude when determining if the value should just, or the neuron should just be shut off as it is. And by using this activation function, we're able to avoid the sake of having only a linear decision boundary. Without the activation function, your neural network would struggle to extend beyond just a linear decision structure. So by adjusting which neurons we decided to leave on or active and having all the rest of them just be off and not worry, we can still conform to the real world scenarios, which in our case was the spiral decision boundary. Aside from that, we used libraries to create tensors for data storage. So these tensors allowed us to store and manipulate the data and made it easier for computing the linear algebra required for the calculation of loss. And for our model, we implemented the softmax loss function. And this way, we used, instead of just any old loss function, we took the most common loss function and implemented it such that for this basic neural network, anyone using the Ada language and wanting to make a neural network could take what is the most common loss calculation and implement it into their project. We also decided with softmax loss because it was one of the least computationally intensive algorithms, such that whenever we are training our model, we didn't want to overrun or flow our model with inessential computations. So by keeping it simple, we can prove that machine learning truly is possible within the Ada language and that there aren't other issues that are just adjusting numbers and getting other results by chance. Another big part of a machine learning model is the optimizer. And for our model optimization, we created and implemented the stochastic gradient descent optimizer. So what the optimizer does is it prevents the model from becoming stuck in a local minima when finding what's called the optimal point. So whenever we're trying to find the least amount of loss, you can imagine that graph, we keep the loss bouncing around trying to escape local minimums before readjusting the numbers on the next cycle. And that way we can inhibit the model such that the results will reflect more and more accurate results, aka less loss. So what was challenging about our project? I really could go on about the challenges related to data handling and calculations and new data structures and algorithms, but the largest conflict was related to the complexity of low-level operations required by Ada. And to illustrate how these issues may arise, what you're looking at here is the basic implementation of machine learning engines forward pass using Python code. So there aren't very many steps in what would be considered this basic function. But a lot is really going on behind the scenes here that wasn't possible within Ada. So what I'll show next is the Ada implementation of the same function. So this required a lot of intricate planning and manipulation of both the data and the memory, being able to take one different data type and make it conform with another, and also use the least amount of memory required. And obviously, with this being the very introduction of machine learning within Ada, there's plenty of optimization within our algorithms that can better utilize either speed or storage complexity. But I feel this image really describes what's going on behind the scenes and something that people are more common with the Python functions. Because really those Python functions are still calling other low-level functions, whether it be C or C++, or hopefully eventually even Ada. But this project is a step in the right direction to getting Ada involved for machine learning in the future. So to overview the architecture of a typical neural network, we had to consider what a neural network looks like and what we wanted our network to be capable of to determine which components we needed to create and be able to interact in specific ways with each other. So to go for this, we decided to include functions to create and add layers to the model. This would be particularly your linear layers where every neuron in the input is connected to every neuron in the output. And by having these layers, we can propagate the data using the forward function. That was the one that I had just shown. And on top of that, we decided to implement the activation function. So we had to create and implement what would be our activation. Shown here is the RALU. We can see all the values of 4, 0, and up to 0 are just 0, and everything after is positive. And by having this activation function, we can make it connect to all of the outputs of one layer and then relate back to the inputs in the next layer. And from here, we needed some form of normalization, and this would go with our loss. In our case, like I said, we'd use softmax loss. So we have our normalization, and what's not shown here is the optimizer, but creating the necessary functions to implement and function and optimizer allowed our different data to be manipulated just for better results. But what's shown on the very right-hand side is what's called backpropagation. And backpropagation is necessary to update the model throughout each run to show how accurate each of the neurons were in contributing to the model's decision. So each feature propagates a specific loss value, and that's what we are trying to measure. So we can use backpropagation to see which values or which neurons were responsible for which specific loss values. So by being able to fulfill this architecture, we can create a better network within Ada natively. So finally, I have an example of our ML engine running on our constructed Ada code. So running it in the terminal, we do our simple ALR run. We loop through many epochs or generations essentially, and each epoch has numerous iterations to best train before moving on to the next epoch where it ideally improves. And finally, we get a resulting accuracy, which, while we can still optimize, being able to have it better than just guessing consistently proves that our model is capable of learning different concepts and can be extrapolated on to different applications. So in terms of applications for this project, while further development and fine-tuning would be necessary, it's not unreasonable to think that these capabilities may contribute to mission-critical systems, as well as functioning parts within larger platforms on other systems. We can either have these systems be fully run on Ada due to different security or safety reasons, which is what Ada strives in, or we could have them run back behind other functions. As I mentioned earlier, ideally, Python could be able to call one of these Ada functions, and it would be the best option. So thank you for attending this presentation. Does anyone have any questions?
Thank you, Owen. It's very nice, and congrats for the full year, and you did an amazing job. Seriously, it would be. We're only missing your teammates.
Yes, thank you.
It's great that you're here. Very interesting stuff. Okay, so we will move on right now to Kien and Stuart. Who will present you the embedded Flexbox project. So Kien, Stuart, the floor is yours.
Hello.
Hello.
Hi.
That's present for everybody. Well, hello everybody. My name is Stuart Walters.
Yeah, Nguyen.
And I will be presenting to you embedded Flexbox. So just a brief overview of what we're going to be covering. We're going to do a brief discussion of what Flexbox is, what our project embedded Flexbox is, and then we'll discuss our target system, Ada, multi-way trees and concurrency and how that relates to our project, a couple of the UI components that we've designed, and then we'll share with you some of the ways that you can customize them to build user interfaces, and then we'll move on to the demo. So first off, what is Flexbox? Flexbox is a layout system that's capable of creating efficient, dynamic, and responsive web page layouts. If you've ever browsed the internet, then chances are you've come across a web page that utilizes Flexbox in order to organize things on your screen. Some of the key features of using Flexbox is having a responsive design. So generally, Flexbox web pages, they'll respond if you shrink or increase the size of a web page. You'll see it visibly change for you. These are some of the things that we'll be trying to capture ourselves. And then obviously there's the ease of use. There's plenty of good properties such as flex direction, justify content, and align items to control your layout. Embedded Flexbox is simply a imitation of Flexbox that's designed to be deployed on embedded systems. We developed it using the Ada programming language, and it makes use of the Ada drivers library, specifically the subset provided by Olivier, to interface with STM microcontrollers. It primarily utilizes a multi-way tree structure to take advantage of Flexbox's behaviors. There'll be more on that later. Shown here is our target system, the STM32F746G discovery board. We program the board using open on-chip debugger, so you would build your UI on a native in a native environment, compile it to machine code, and then send that machine code to the board to run the user interface. We utilized Ada for many reasons. I mean, first off, we were supposed to, but joking aside, Ada is really great for this because its strong typing makes sure that when you define different widgets, they are well defined and they're used properly. Rigorous compile time checking done by Ada ensures that when a user interface you design compiles, it will run properly on the board. And then obviously Ada comes with many advantages with concurrency that we can take advantage of that we'll be discussing in detail later on. But obviously you have the low-level resource control provided by the Ada drivers library that we utilize. And then we make use of Ada libraries such as the containers library for its multi-way tree and the real-time library to be able to do timing constraints on our tasking. The multi-way tree is the foundation of embedded Flexbox. So if you imagine a web page, you have a series of like buttons and images and everything that kind of act as layers on the screen. And the screen is built as a series of layers. And a tree is very good at capturing that behavior. So the farthest up root node can behave as sort of the background of the screen, and you just kind of paint more layers onto the screens. And the multi-way tree does a good job of basically allowing us to capture that behavior of sort of painting layers on a canvas. So on the right side, you have an example tree with a parent, 2 child nodes, and then a couple of grandchildren. And then we made sure to label them properly on our screen as well. So you can kind of see in action, we have a parent, and then the child's paint on top of the parent, and then the grandchildren paint on top of the children. So yeah, the multi-way tree, it has a hierarchical structure. So any one parent can have any number of children. That's fantastic. That's exactly what we need for Flexbox, because any one portion of your screen when you're looking at a web browser could have any number of elements. So this captures that well. The multi-way tree specifically in Ada is very flexible, so we can add, remove, rearrange, edit any node during runtime very easily thanks to all the functions and procedures that are provided by that library. And also there are many ways to quickly access specific portions of the tree for manipulations as well. It's very fast, it's very efficient, and yeah, it's good stuff, Ada, good stuff. Yeah, so concurrency, our system is split into 2 tasks. You have a user input task and a render frame task. They each run at their own set time intervals, and they communicate using Ada's protected object. So when a new frame is being rendered, it will basically access this protected object that's being written to by the user input frame to basically ask it, hey, has a user input occurred in between frames? And if it has, then the render task can kind of react to that input to make sure that the most up-to-date user input is displaying on the screen on a given frame. Shown on this screen is just a list of some of the UI components. So we have a standard widget, which would more often than not be used as like a standard container to contain any number of other widgets. The button, image, and text widget each behave as sort of children of the widget. So when you're inserting widgets to your sort of tree of widgets to display your user interface, you can input things such as buttons, which basically have an event call that you can customize by subclassing the button. So you press it and it just runs some function that does whatever it is that you need it to do. You have the image widget, which takes PNG files that you basically load as source code in your native environment and then shoot to the board. No external storage is needed to load the images during runtime, as you'll soon see. And then we also have the text widget, which prints text onto the screen. You'll be seeing that. You've seen that, and we'll be seeing more of that in the future. Some of the parameters that you can manipulate include sizing. So on the right, you have an example image. It shows you just a series of widgets with the different sizing behaviors. You have the pixel, which is a static behavior. So you have a 20 by 20 pixel little square there. So we wanted the widget to be that size, so it is that size. It's static. So if the size of the container that it's in were to change, the pixel, the actual widget itself will not change unless you shrink past its size. We also have percent. Percent takes up a percentage of the parent container. So in this case, that particular percent widget is taking up 10% of the width of its container and 50% of the height of its container. Portion is a behavior that's relative to sibling widgets. So in that particular row, you have a purple and cyan widget. The purple widget is given a portion of 1 and the cyan is given a portion of 2, meaning that for every 1 pixel that we provide the purple widget, we're providing 2 pixels to the cyan widget. And as you can see in the image, the purple widget takes up roughly 1/3 of the space, cyan takes up 2/3 of the space. The max behavior is a little more interesting. You're basically instructing the widget, I want you to take up any remaining free space that may be available. So in this instance, because that green widget is the only widget in that given row, it takes up the entire space. But if there were other widgets with their own settings, they would be resolved first, and then the remaining space after the fact would be distributed to that widget. So as an example, if there were 2 max widgets, it'd be 50% evenly distributed amongst those 2 max widgets. And if there were just like, any other setting, they'd be resolved, and then the max widget would take up the remaining space. The last sizing behavior that we have is content. Content is a behavior that's unique to parent widgets. What you're essentially instructing the widget to do is to only take up the space needed to encompass the child widgets that it contains. So in that row, you'll see a purple, blue, and pink widget. And then sort of around it, you'll see like a cyan widget. You notice how the cyan widget doesn't stretch all the way across to the opposite end of the screen. It stops right at the border of the pink one because that's the only amount of space that it needed to take up. And the same can be said for the height. So you have that blue widget that kind of juts out a little bit more than the other two, and you can see the background cyan widget kind of peeking out and saying hello. Yeah, you're basically telling a parent widget, I only need to be the size that my children need. To continue on different parameters, you can set the direction. This basically instructs the parent widget on how to display its children. So you can do different row settings, such as left to right and right to left. And you can do column settings for top, bottom, bottom to top. The different directions is basically just the direction at which the children will display. We have different spacing behaviors. The first spacing behavior that we have is gap. So we have row gap and column gap. This is a static spacing, meaning that if the size of a given container, if it increases or decreases, this spacing will stay the same. It will always try to give a set number of pixels. In this case, I believe it's like 5 or 10 pixels on the image, but we have it labeled. You have your column and your row gaps shown here. We also have buoyancy, which is effectively justified content. This is a dynamic spacing. When the widgets are calculated and distributed, we take the remaining space in a container, and then we apply a given algorithm to apply that free space between the widgets. On the right-hand side, you can see two of the different algorithms. We have space evenly and then space between. But if you don't want to apply any free spacing, there's space nothing in case you don't want to use that free space. But in this case, because it's dynamic, if the size of the container were to change, increase or decrease, we would either increase or decrease the distance between the widgets because we will increase or decrease the available free space after calculating sizes of the widgets. And then the last parameter that we'll show here before going to demo, we have alignment. This basically manipulates the positioning of the widgets in a given container. So top, bottom, left, and right simply place the widgets at the specified border. And then the center centers them in the parent, and stretch stretches the child to the size of the parent. We have a couple examples on the right there for you to see, but you'll be seeing more of that later on. We'll now be moving on to our demo.
Hello again, I'm Kien, and I'll be demoing our project. So as you can see here, here's our STM32 F746, and we have loaded here a demo of our project. So the squares and rectangles you can see here are our widgets. We have some basic ones here in the center. Then at the top we have some button widget with some text. And when I can press one of them, so this left one will change the alignment, and as the widgets here went from center to bottom to stretch, top, and then back to center. Equivalently, we have buoyancy, and when I press this one, it changes from space around to space evenly, space between, then space nothing, and back to space around. And finally, for the third button here, we have direction. Currently, we're in the left-right. Then we go right-left, top-bottom, bottom-top, and back to left-right. Other things that we can do here is I can drag with one finger here. So, a bit tricky. Sometimes a little bit hard to get the border of the widget sometimes. There we go. So with one finger, I can drag widgets like so. I can also resize with two fingers. And as you can notice, with the buoyancy, when I'm resizing it, it will dynamically change to allocate the spacing appropriately. Give me a second for me to load up another demo to showcase our images. So I can see when the screen goes white, that means a program is being loaded. You can also tell by the blinking LED here that a program is being loaded on there. There we go. This is our image gallery demo. And see here, we have some images here at the top here, and the center one has a label under it as with a text widget. And then at the bottom, we have a button labeled Change Me. And when I press it, it will cycle through the images at the top here, as well as changing the label to correspond to the right images. I can also resize the images like so. and the sizing will stay the same even as I change between images. And yeah, that's it for our demo. I hope you enjoyed it and our presentation.
We would like to take any questions that anybody may have now.
Is there a way to build, run, view, and interact with the GUI on the native development system? For speeding development, deploying, and testing on the embedded target is usually slower.
And yes, there is. Initially for this project, actually, we started on native, and we're using the X11 as a way to project it and test it out. Like a lot of the features that you saw on the board, we developed on the native Linux development area, and then after in the second half of our project, we transferred to embedded, so then we can start getting those functionality and then fine tune anything that I may have had some bugs that weren't visible in native or were in embedded, because of the how we didn't have quote unquote touch interaction on native. We had some interesting bugs with that here on embedded, but yeah, we do have a native version that we use to develop first.
Other questions? Do you plan to develop it into a library?
That would be interesting. I'm certainly interested in doing it. If I were to do that, I would probably take a step back and change some things. There were definitely decisions made in the development process, mainly due to timing constraints with the project. But yeah, I'm interested. I'm interested in making it into an actual library. And something that just for the previous question. The native build is a bit older, but the engine itself is designed to be as independent from its environment as possible. So when he was discussing the native build, yes, we use the X11 Windows system. It's literally just to be a window. Everything that has to do with actually building the image to put onto the screen, done on its own. So in an ideal world, if we were to develop it further into a more fully fledged library, all you would have to do, hopefully, is basically just kind of insert whatever your little window is, and then the library would be able to output the image. But to answer your question, yes, I am interested in making it into a library.
Cool. It's good news because Fabien would love to plug that with RayGUI. So this is good news. Is the memory allocation static, or does it require dynamic allocation?
That is a good question. We didn't play too much with creating widgets at runtime, but in theory, you should be able to do it, and I would assume that it would have to be dynamic, not static.
I can answer that though.
Hmm?
I can answer that. The multi-way tree by definition is handling behind your back dynamic memory allocation.
Oh, thank you. See, it was skipping my memory. Yeah, thank you. Yeah, the tree kind of handles some of it for you. Yeah, thank you, Olivier.
But I think, maybe Fabien can correct me, I think we could use a bounded multi-way tree so that it reserves a maximum number of memory and then plays with it.
Yes. So the system itself is like, let's say 95% Ada. If you are playing around with images, there is a Python script that we borrowed from another Ada project that had the wolf demo. The name escapes me at this time.
Doom, yeah.
Yeah, we borrowed the Python script from there, but we actually don't use YAML or anything. It's aside from that one Python script that's used to basically just turn a PNG into an ADS file, it's all Ada.
Mm-hmm.
It's 100%.
Yeah, Jérôme Lambourg did that, those demos.
Yeah, well, thanks to him, he saved us a lot of time.
Good. Okay, well, is there any other questions? Looks like it's good. Well, first, thank you very much. You can be proud. It's amazing. It's super great showcasing that stuff. It's interesting, captivating. I really loved your project. I loved all the project, but I want you to. It was fun. So thank you very much for
Thank you.
that. Thank you for
Thank you.
presenting. Yeah, it showcased Ada in a very good way, I think. Okay, so now let's move on to the next presentation and the last one.
Okay.
Samuel from Université d'Ottawa cannot be here with us today, so he did a pre-recording. So I will share the video with you, the presentation of his.
Hi everyone, I'm
Whoa,
Samuel.
whoa, whoa.
I just recently graduated from the University of Ottawa,
Here it
and
is.
today I'll be presenting to you guys my bare metal implementation of the MIN protocol for easy communication. So just to start off, so everyone kind of understands what a communication protocol is, let's just go with a little bit of an explainer here. So what is a communication protocol? Well, just put very simply, it's a set of rules for how two things should communicate. In this case, we're dealing with two computers that have to talk to each other. And you can think of a communication protocol as like a language that both computers can understand. Now that we know what the communication protocol is, well, we can talk about the MIN protocol itself. So the MIN protocol was actually created by Dr. Ken Tyndall all the way back in 2014. And MIN actually stands for Microcontroller Interconnect Network. So just from that name alone, you can tell that it's a protocol that was designed mainly for use with microcontrollers. And just to kind of explain what the purpose of this protocol is, well, this is taken directly from the GitHub page for the protocol, but it says, MIN is a lightweight, reliable protocol for exchanging information from a microcontroller, also known as an MCU, to a host. Essentially meaning that it's a very simple and low memory or low computationally expensive way to send data between two computers. And we would use, it was mainly designed for use with microcontrollers such as the STM32F429 that I have right here. And if you guys want to learn more about the protocol itself, if there's any information or any questions that you have that maybe information that I haven't mentioned, you can always refer to the GitHub page for the protocol, as you can see on the bottom of the screen here. As we can see on the right side of the screen, the MIN protocol is actually composed of 3 layers. Let's start with the bottom layer, the serial layer. So the serial layer is essentially the bridge between the MIN protocol and the underlying serial link between two devices. Essentially, its purpose is to take the data that we are sending and send it byte by byte over the serial link. In this case, I was using UART, but there could be some other options that you can use here. But just to keep this simple, it's a UART serial link, and all the data sent byte by byte, and on the other end, so the one that's receiving, well, it's received byte by byte, and the pieces have to be put back together after. And this is where there could be a slightly different implementation based on the platform. Like, for example, on the microcontroller, there's a little bit more work that needs to be done because there's no easy-to-use library that's available for it. So you kind of have to use your own implementation of the UART protocol. But on the laptop side or on the computer side, you can use the GNAT serial communications library. And so on the laptop, it's a little bit simpler to implement the serial layer. So this is kind of the part where there's a little bit of work that needs to be done on your part as you're implementing the protocol into your project. The part that does not change, however, the frame layer. So the frame layer is responsible for packing and unpacking data within frames. So each frame contains a bit of information about the data that we're sending. So it contains an ID, which is essentially just an arbitrary number that we can use to identify maybe what sensor the data is coming from. This is completely up to you to decide as you implement the protocol. You can have your same application send data over multiple different IDs. It's not random per kind of transaction or per frame that we're sending. It's more based on your needs. So you can choose to always send using the same ID, or you can use a different ID for the various different sensors that may be connected to your microcontroller, for example. We also have information about the length of the payload. Obviously, the payload itself is also included in the frame, And at the end of the frame, we also have a checksum, which allows us to perform some basic data integrity checks. So as already mentioned, frames have a special start byte to kind of tell the receiver when our frame is starting, and they also have a special end byte to tell the receiver when the frame is complete and it's fully received. And in certain cases, it may happen that the data kind of looks like one of those start or end bytes. So we're going to use a technique called byte stuffing, where we're going to insert another special byte right before any part of the data that might look like one of those bytes, so that the receiver can tell that this is not supposed to be one of those start or end markers, and in fact is supposed to be part of the payload. So anytime we have anything that could confuse the receiver, we'll put this special byte stuffing byte to tell the receiver to basically ignore this next byte coming in. And the frame layer here, if using the checksum, can tell if the data is not correctly received or if there's some sort of corrupted data, in which case it will simply just drop the frame and the data will be essentially lost. But if we do receive a frame and it passes the checksum, then a callback function is called in the application, and then from there, as you implement the protocol in your project, you can choose to do whatever you want with the received data at this point. And finally, we have the transport layer. Now, this is an optional layer. In fact, we don't need to implement this in the base Min protocol implementation. This is actually not really a part of it. But for certain projects, this is a layer that could be useful. Essentially, what it does is it ensures that the frames that are received are correctly received and fully received. Otherwise, they're requested to be sent again from whoever sent the data. So like I already mentioned previously, we use the checksum to verify that the data has been correctly received. So in this case, if we choose to, we can implement this layer and request the data be sent again whenever there is any problems with the frame. In my case, I didn't implement this layer just because I was kind of limited with the amount of time that I had to work on this project, so my implementation specifically does not include this layer. So now I can talk a little bit about my project, what I did. So the Min protocol is obviously already an existing protocol, so what is it that I did? Well, Min was only implemented in C and Python, and this was done by Dr. Tyndall, and there's also a Rust implementation that was done by a third party, but it was not available in Ada. And Min is a great protocol for embedded projects, and it's lightweight, it's simple to implement, so it just made sense to bring this protocol to Ada. So a few goals with this project was to provide the Min protocol as an easy-to-use Olivier package. That was the main goal with this, but it also served as a way to kind of learn more about communication protocols and also as a way to familiarize myself and learn a new language, because I had never worked with Ada before, so this was my first experience with the language. So of course, working on this project, there's always a few challenges. So one of the first challenges, of course, because this was a new language and I wasn't familiar with Ada, obviously all the challenge of learning a new language and learning how to use the different parts of the language, that was obviously a challenge working on this project, especially with the limited amount of time. But also, because the protocol already exists, I can't just go around doing whatever I want with the protocol, so I kind of had to follow what the protocol was already doing through these other implementations, whether it be the Python or C or Rust implementation. So obviously I have to understand how the protocol works to be able to implement it properly on the Ada side. And finally, just developing for embedded systems in general can be difficult to debug because these types of microcontrollers are usually a little bit more limited in the type of software support that they have. So sometimes you don't have the most extensive tools to test out your project. So sometimes the errors that these microcontrollers can throw can be a little bit more generic, a little bit harder to understand. And not all microcontrollers have a screen like this one does. So sometimes if you don't have a screen, it can be a little bit harder to debug as well. So there's obviously always some challenges with working with embedded systems. So now let's actually just take a quick look at how we can implement the Min protocol in our application, as well as a quick little demo. So let's switch over to my VS Code window, and I'll show you guys how this works. All right, so now let's take a look at implementing the Min protocol within our projects. So depending on what serial communication you're going to use, you're going to have to implement that part yourself. So in my case, I'm using this UART for board package, which is a custom implementation of UART on the embedded side. This is kind of falls outside of the scope of the protocol itself, but this is provided on the GitHub page, on the GitHub page for my project, which you can see on the GAP academic GitHub organization. So if you want to take a look at the implementation for that, it's going to be available there. But otherwise, we have to implement the min-ada package, which is where all the main min protocol logic happens. And this my min-ada in this case is a package that I also wrote myself, which serves to. But otherwise, we have to implement the min-ada package, which is where. But otherwise, we have to implement the min-ada package, which is where all the main min protocol logic happens. And this my min-ada in this case is a package that I also wrote myself, which serves to provide some of the functionality of the protocol in our application. So this is actually where we can override the handlers, which is essentially the behavior of what happens when we receive data and when we're sending out data. So the first thing that we do is obviously we have to initialize our serial communication, which is what we do right here. So this is going to be a little bit different depending on how where you're doing this or where your project is going to be deployed. And then we can initialize min. So all we do is we call the min init context, and we provided a context in which the min protocol can use. And essentially the context just serves as a way to kind of keep information about what's going on, what are we receiving, what are we sending. It just keeps the state of the protocol. Next, we have to override two things. So there's this min application handler that we have to override, which is essentially the handler for when it receives a full frame of data. Once it's received all the parts of that data, this procedure is what it would call, this callback function. And then from there, we can do whatever we want with the data. We can also override this tx byte if we plan on sending data. This tx byte procedure essentially just sends out 1 byte of data. And essentially in this procedure, we implement our serial communication. So in my case, just to show you an example, in my case, my application handler here, all we're doing is we're taking the payload that's received at the top here, and we're just putting the pieces back together into one string, which is, in this case, I just call message, and then we're displaying this message on the screen of the microcontroller. And for the tx byte part, the data is the byte that we want to send, and then we're just saying, okay, send this byte over our UART implementation in this case. So next, let's take a message. So in this case, I just have the string hello AdaCore that I want to send over, and this is going to be the payload buffer that we're going to put this message into. So this is what this part here does, is it takes our message, splits it up into the numerical representation of each one of those letters, and puts them in this payload so that we can send it out. Then we call min-ada send frame to send out the payload. So we provide the payload, the app ID, which again is an arbitrary number. Also provide the context, of course. And we also just have to tell it how long the payload is. So in this case, just the length of our message. Then in our case, we can just inform the user that the data was sent. And then we just go into this loop and we wait for data to come in. So in my case, my project, all it does is it just sends the data out from the microcontroller to the host, and then the host sends the data back to us. So here we would be kind of waiting for the data to come back, and it would come back to us 1 byte at a time. And then we would take each one of those received bytes, which we just store in received data here, and then we send it directly to the min protocol here by calling min-ada rx bytes, and we provide it the context, the min context, and that data that we just got. And then from there, once all the data bytes are received, that's when it would call this min application handler that I mentioned earlier. And that's essentially, that's how you implement the min protocol in your application. It's really quite simple. So it's really just a few functions, 1 or 2 functions, like one to send and one to receive. It's not very complicated, but it works very, very well. And I'll just show you guys a little demo of me sending this data on the microcontroller and on the host side as well. So now let's take a look at the host side and see what we have here. So essentially, this is pretty much the same as the microcontroller side. We're using GNAT serial communications for the UART implementation, but otherwise the behavior of the application is essentially the same. There's a few minor differences, but overall, the implementation for how we actually implement the protocol functions and overriding the handlers, this is all exactly the same. So we can see here that we have those overrides and we have this init context. So all of that is the same. So we can just run the program over here. So let's run the actual program. And now it's waiting to receive data. So now if I just reset my microcontroller so that it starts the program over, we should see that it should receive the hello AdaCore message. And we can see that we received that message, and we even see all the bytes coming in one by one. So this is just for demonstration purposes, of course. I decided to show what bytes we're receiving, but essentially we see these are actually our start bytes. We're sending 3 in this case for redundancy, but these are the special start bytes, and then we have some additional metadata about what's being sent, and we also have the payload here, which is the actual message itself, and then finally we end with this special end byte that tells us that the frame is completed. So we get the message, hello AdaCore, and then once we've received it, well, we are sending the data back. That's what we're seeing here. We are sending, it's basically taking this message and packing it into a frame and then sending it back. But what we're sending out here is the same thing that we received as well. In fact, I can even pull up a terminal window here. Let's make this a little bigger. And if I run the screen command, which allows us to kind of inspect what's going on the serial communication. So let's just point it to our microcontroller board. And we have to set a baud rate. So we're just going to use the default here. So now if I reset the board again, we should see what we're receiving on serial communication. So as you can see, we have those start bytes and some of the extra metadata that's at the beginning of the message. Then we have the actual message, and then we have the checksum and the end bytes here. So we can actually see that this is what we're seeing on the UART communication link. And just to finish off the presentation here, so obviously there are some things that could be improved about the protocol, or at least this implementation of the protocol. And the main thing that could be added is that transport layer that I already mentioned. I didn't have time to add, so this could be a possible future enhancement. Second thing would be to finish packaging the library. So as it stands, it's not actually an Olivier package yet. So all the pieces are there essentially, but it just has a little bit of work that has to be done, and it has to be published on the Olivier index so that people can just quickly install the library and use it, or the package, sorry. Another improvement, provide clear documentation. So as of right now, there's basically no documentation of how to use the package, so that would be an improvement, of course. And finally, because this was my first time working with Ada, there's probably some things that I might not have done in the most optimal way. So there's obviously probably some optimizations that can be done to the protocol to work better overall. So that's it for me, guys. I thank you so much for watching this presentation. Hopefully this was interesting to some of you, and I just want to give a shout out to all the people over at AdaCore. I had a really good time working on this project, and specifically Olivier, who helped me out throughout this project and helped me with all my Ada related problems. So just thank you to you and to everyone over at AdaCore. All right, that's it for me, guys. Thank you.
Okay, sorry, I was mute. Okay, my bad. Samuel, if you listen to this recording afterward, I want to thank you. You did an amazing job, an amazing presentation too. It was a blast to work with you. I want to point out to people it was a 1 semester project, and 1 semester flies really quick with the exams and everything. Sam was great. Yeah. So that's it for us. Thank you everyone for attending. I hope you saw and found interesting things happening here. I want to thank everyone, first AdaCore, for being open to that kind of experiment and going forward with those capstones. I want to thank everyone that worked really hard, all students. You can be very proud. Ada is not easy. Ada is strict. Ada is many things, but not necessarily easy, right? You showed a lot of commitment, a lot of professionalism. I would hire you all in a heartbeat. So that's it. We stay in contact. Anyhow, you can contact me anytime. So everyone, if you have questions about GAP or even AdaCore, don't hesitate. You can contact me, and please visit our webpage. We will follow up with the link for this video, and also if you have specific questions, we can answer on an individual basis. So that's it. We're 5 minutes late on our agenda. I hope you enjoyed. I wish you a great day. Thank you, everyone.